Today we're going to talk about limits as we approach infinity, or limits as we approach negative infinity. In other words, what happens when the x values increase or decrease without bound. So we're just going to real quickly think about this first function here, 2 plus 1 over x. And think about what happens as the x values get very large. What happens as x goes towards infinity? What's the limit of our function? Right? What y value are we approaching as the x values get exceptionally large? Well, if we think about this, really what we're normally doing with the limit is we're just plugging in the x value, right? Well, our x value is infinity. It's not really a number. We can't exactly plug it in, but we can think about what happens if I do 1 divided by an infinitely large number, right? If the denominator of a fraction gets bigger and bigger and bigger, that fraction gets smaller and smaller and smaller. And so as x goes towards infinity, this piece right here, 1 over infinity, effectively, should be going towards 0. So really what we end up with here is just the limit as x approaches infinity of 2, right? Which is just 2, right? As x goes towards infinity, 2 is just 2, and 1 over x is 0, so we just end up with 2, which is telling me that for this particular function, as x goes towards infinity, the function should be approaching a y value of 2. And so we should, in our heads, when we hear this, we should think, oh, we're talking about a horizontal asymptote here. So real quickly, I'm just going to flip over to Desmos here. And if we put in 2 plus 1 over x, we should see that this function is going towards 2 as x goes towards infinity, right? I could even put in, y equals 2 here. And we could see that if I scroll over here, as I go towards infinity, as I get bigger and bigger and bigger, that function is going towards y equals 2, right? And in fact, it's actually doing the same thing on the other side. As x goes towards negative infinity, the exact same thing is happening, right? This function is still approaching a horizontal asymptote of 2, right? So that's what's going on here. When we talk about a limit as we approach infinity, or a limit as we approach negative infinity, we're talking about horizontal asymptotes. Right? We're talking about how that function behaves as the x value gets very large. That's a horizontal asymptote if we get a numeric value for it. So let's sort of look at some basic ones of these. We're going to start with some rational functions. Rational functions is probably where you've most often dealt with limits, or not with limits, but with in behavior and with horizontal asymptotes. You may not have actually looked at them as limits, but we're gonna do that today. So if we want to use limits to determine if this function has a horizontal asymptote, we're going to do a limit as x approaches infinity of our function, 2x squared minus 5 over, in this case, it's 3x squared plus x plus 2. Now, if I try to plug infinity in, I end up with infinity squared, which is infinity, and I multiply that by infinity, right? Multiply that by 2. 2 times infinity is infinity. If I subtract 5 from infinity, I still get infinity, right? And same thing happens in the denominator. Infinity squared times 3 is infinity. If I add another infinity, it's infinity. If I add 2, it's still infinity. This is infinity over infinity, which is one of our indeterminate forms from our long list of indeterminate forms that we looked at about a week ago. So we have to come up with a method to deal with this particular indeterminate form. And so it's going to be a new technique here. What we're going to do is we're actually just going to look for the highest degree of either of the polynomials, whether it's in the numerator or the denominator. In this case, the degree is the same, right? Both the numerator and the denominator, the highest power is 2, right? So the degree of both of them is 2. So the highest degree overall in this rational function is 2. So what we're going to do is we're just going to divide every single term in both the numerator and the denominator by x to the power of 2, that highest degree. So we'll say this is equal to the limit as x approaches infinity of 2x squared over x squared plus minus, let's fix that, minus 5 over x squared, all over 3x squared over x squared plus x over x squared plus 2 over x squared. And now let's simplify each of these pieces. And this is perfectly legal, right? We can multiply the top and the bottom of a fraction by the same thing, right? Because it doesn't change it, it's multiplied by 1. This is the same thing. We're just dividing by the same thing to the top and the bottom. And this is effectively exactly the same. So 2x squared over x squared just becomes 2. So we've got a limit as x approaches infinity of 2 minus 5 over x squared. All over, well, 3x squared over x squared is just 3. X over x squared is just a 1 over x. And 2 over x squared is also just 2 over x squared. And so now, this is starting to look similar to the limit we looked at on the previous page, where I've got some constants, but I've also got some other constants that are being divided by things in terms of x. And as x goes to infinity, those things in the denominator there are going to get exceptionally large, which means those fractions are going to get exceptionally small. In fact, they're going to get exceptionally close to 0. They're going to get insignificantly small, right? 5 divided by infinity squared is effectively 0. 1 over infinity, 0. 2 over infinity squared, 0. And so we're just left with the limit as x approaches infinity of 2/3, which is 2/3. Now, what this has shown us is that this particular function has a horizontal asymptote of y equals 2/3 to the right. Now, it's very important that we specify that this is a horizontal asymptote only to the right, right? Because we looked at a limit as x approaches positive infinity. And so we need to also investigate what happens as we approach negative infinity. Right? Some functions might have a horizontal asymptote in only one direction, or they might have different horizontal asymptotes in different directions. So we really do need to look at what's going on as we approach negative infinity. And anytime you're asked to find all of the horizontal asymptotes of any function, you have to show a limit towards infinity and a limit towards negative infinity. So since I'm kind of out of room here, I'm just going to do this here. We'll do a new page. A limit as x approaches negative infinity. Let's see here. I've already forgotten what it was. It was 2x squared minus 5 over 3x squared plus x plus 2. Now we're going to follow the exact same process. I'm just going to divide everything by x squared. Now this time when I do that, I'm just going to skip the intermediary step here where I actually do the division, and I'm just going to skip right here to this one, because it's just the post-simplification. That's the simplification within the limit. It doesn't matter what limit I'm approaching to do that simplification. So if I divide 2x squared by x squared, that's just a 2. And the 5 by x squared is 5 over x squared. And the 3x squared divided by x squared is 3. And the x divided by x squared is 1 over x. And the 2 just becomes 2 over x squared. So effectively, all I did was really skip that intermediary step from the last one because it's the exact same step that I had just done. And now we can see that whether I'm approaching infinity or negative infinity, these three fractions that all became 0 last time are all still going to just become 0, right? Whether I have negative infinity and I squared, that's still infinity. Or if I have 1 over negative infinity, that's still 0. Right, so this limit just comes out to be 2/3. And so this will tell us that we also have a horizontal asymptote of y equals 2/3 to the left. And it's very important that we distinguish the, the one to the right and the one to the left. Now, for a rational function, I'm going to tell you this right now. This is important. For a rational function, if a function has a horizontal asymptote to the right, it's going to have one to the left. And they're going to be the same every single time, if it's a rational function. Okay? Now, if this was the AP test and they said to justify the horizontal asymptotes, you still need to show the work for infinity and for negative infinity. Okay? If it was a multiple choice question, then you could just go through and answer without showing all the work. But if it's a free response, you got to show the work. So if it's a rational function, they're going to be the same. If it's not a rational function, well, then who knows? We'll have to figure that out as we go. So for this one, we got y equals 2/3 to the right and y equals 2/3 to the left. It's y equals 2/3 in both directions. All right, so our next one, another rational function, which tells us that when I do this to infinity and when I do this for negative infinity, they should come out to be exactly the same. So we're going to start off by saying this is a limit as x approaches infinity. We'll do infinity first, of 2x squared minus 5 over 3x to the 4th plus x plus 2. And we're going to use the same rules we did last time. We're going to look for the highest degree of either of the polynomials. Well, in this case, because we have a 3x to the 4th, our largest degree is 4. So instead of dividing everything by x squared, like we did the last time, we're going to divide everything by x to the 4th power. So this becomes a limit as x approaches infinity of 2x squared over x to the 4th minus 5 over x to the 4th over 3x to the 4th over x to the 4th plus x over x to the 4th plus 2 over x to the 4th. And now we can simplify a bunch of the terms within there. This gives us a limit as x approaches infinity of, well, 2x squared over x to the 4th is 2 over x squared and minus 5 over x to the 4th. And then we've got 3 plus 1 over x cubed plus 2 over x to the 4th. And now this time, as we go towards infinity, we can see that the 2x squared and the minus 5 over x to the 4th are both 0. And the 1 over x cubed and the 2 over x to the 4th in the denominator are both 0. So this just becomes a limit as x approaches infinity of 0 over 3, which is just 0. So this one has a horizontal asymptote of y equals 0 to the right. So I'm going to write that here. We're going to say y equals 0 to the right. Now, this is a rational function, and so I've already said it's going to be the same as we go towards negative infinity, but it'd probably be good if we showed that. If you want all the points on your test, when you're asked to justify horizontal asymptotes, you better show it in both directions. So it's going to end up starting off the same. We're going to have 2x squared minus 5. We're going to have 3x to the 4th plus x plus 2. And we're going to divide everything again by x to the 4th. I'm going to skip this step in my writing here. I'm just going to go straight here. It's now a limit as x approaches infinity, negative infinity, of 2 over x squared minus 5 over x to the 4th over 3 plus 1 over x cubed plus 2 over x to the 4th, which is just that limit as x approaches negative infinity of 0 over 3, which is 0, which tells us that y equals 0 is a horizontal asymptote to the left, which we already knew, but we've now proven it using the limit. So we're going to do one more easy rational function one. We're going to look at 2x cubed minus 5 over 3x squared plus x plus 2. So as we start this one out, we'll do the same exact process. We'll do a limit as x approaches infinity of, I'm going to be a little lazy here. I'm going to just write of f of x, just so I don't have to rewrite that whole function. I'm going to look at it and say, okay, the highest degree in the numerator is 3, the highest degree in the denominator is 2, therefore the highest degree in the whole function is 3. So I'm just going to divide everything by x to the power of 3. So that'll be 2x cubed over x cubed and minus 5 over x cubed all over, well, 3x squared over x cubed plus x over x cubed plus 2 over x cubed. And now we just need to simplify each piece of this. This is now a limit as x approaches infinity of, well, 2x cubed over x cubed is 2. So we have 2 minus 5 over x cubed. And in the denominator, 3x squared over x cubed is just going to be 3 over x plus 1 over x squared plus 2 over x cubed. And now, as we go towards infinity, the only constant that we're going to have left is going to be that 2, and everything else. In fact, I didn't really need to write my limit there because I'm now evaluating it. This is just equal to 2 minus 0 over 0 plus 0 plus 0, or 2 over 0. Well, 2 over 0, we can't do 2 over 0. This limit doesn't exist. In fact, it's going towards infinity, right? If I was thinking about this as a limit, right? This ends up equaling positive infinity, which tells us that this does not have a horizontal asymptote, no horizontal asymptote to the right. Now here's the one little caveat to the rational functions having the same asymptotes. It's true that this won't have a horizontal asymptote to the left, but it is possible that this function, as we approach negative infinity, right, it might actually be approaching negative infinity. It might not be, but it might be, right? So just because one comes out to be positive infinity doesn't necessarily mean that the other one's also going to come out to be positive infinity as well. It might come out to be negative infinity. So since we do need to show our limit as x approaches negative infinity, let's do that. And I'm going to be a little lazy again. I'm not going to write this middle step here, right, because it's not really that necessary. I know I'm dividing everything by x cubed, so I still get the limit as x approaches negative infinity of 2 minus 5 over x cubed, and then over 3 over x is what we got there, right? Plus 1 over x squared plus 2 over x cubed. And so now if I think about what's happening as x goes towards negative infinity, well, the top is just going to become 2. And in the bottom, I've still got a 0 plus a 0 plus a 0, which ends up being infinite. Now the question is this a positive infinity or is this a negative infinity? And we should be able to think about this in terms of like what's going on with this very first term here, right? 3 over x, that's actually going to be when I plug in something very large to the denominator. This number is actually going to kind of dominate these other two, the 1 over x squared and the 2 over x cubed. 1 over x squared is insignificant by comparison to 3 over x when x is really large, just as 2 over x cubed is as well. So these two things are even closer to 0 than this is, and this thing happens to be negative when x is approaching negative infinity. So really what we're looking here at is this is becoming negative infinity, right, which is telling us that this function is decreasing without bound as the x values approach negative infinity. So we ended up with a positive infinity the last time, but a negative infinity this time, but the result is still the same. There's still no horizontal asymptote. Right? We don't have a horizontal asymptote to the left. We don't have a horizontal asymptote to the right. This function has no horizontal asymptotes. And that's a rule that we're going to, we'll talk about it again. You should have learned that rule in your previous math class about horizontal asymptotes for rational functions, but if not, we'll rehash it in just a bit. Before we go back through that rule, though, let's take a look at a special case. It's not really a special case, but a slightly more complicated case that does relatively often show up, especially in the multiple choice on your AP test. But we're going to kind of look at two different ways to go about this one. But if we're looking for horizontal asymptotes, we know, first of all, that we need to do a limit as x approaches infinity of the function. Right, so let's do that. And then we think, well, this is, number one, this is not a rational function, which means that we're not guaranteed that the limit as we approach infinity is going to equal the limit as we approach negative infinity. So we got to keep that in mind. And also, there's not really like exactly a highest degree going on here. But there sort of is, right? If we look at the numerator, it's got an x squared, but it's within a square root, which is effectively like a power of 1. And the denominator effectively also has a power of 1, right? 4x to the first power. So it stands to reason that I might want to just divide everything by x, which is great. We can do that. And I'm going to write out what we're going to do, and then we're going to talk a little bit about it before we actually do it. Right? I'm going to write it out in this way. I'm going to expand out that square root into 9x squared plus 2. And I'm going to actually divide both of these things by x squared. But I'm doing it within the square root. So if it's a square root of x squared, it's effectively like an x, but it's not exactly x. So we're going to talk about that in a second. And then over here, I got 4x, which I'll divide by an x, and a 3, which I'll divide by an x. So this is kind of going to be our start here. But let's talk about why we can do this, right? Because really, up in the numerator, I'm actually dividing by the square root of x squared. And hopefully you remember that the square root of x squared is the same thing as the absolute value of x, right? That's something you should have learned about in the previous math class. Square root of x squared is the same as absolute value of x. So in the top, I'm dividing by absolute value of x, and in the bottom, I'm just dividing by x. Well, in the case where x is greater than 0, really for x greater than or equal to 0, the absolute value of x is just equal to x. And we are doing a limit as x approaches positive infinity, which indicates that x would be greater than or equal to 0. So what we've done here is perfectly legitimate. But in a minute, we're going to do a limit as x approaches negative infinity, which means this is not going to be the case, which means that we can't just do what we did. We're going to have to figure out something else to do. So for now, we're good. So let's just deal with this. We'll worry about our future problems in the future. So 9x squared over x squared is just 9. So I've got a square root of 9 plus 2 over x squared is just 2 over x squared. And in the denominator, I've now got 4 plus 3 over x. And so as I go through with this here, well, as x goes towards infinity, 9 is just 9, but 2 over infinity squared is very close to 0. And so this becomes the square root of 9 plus 0 over 4 plus 0, which is just 3/4. Right? So we end up with a horizontal asymptote to the right of y equals 3/4. So we're sort of halfway there. Okay? Now let's see what happens if we try to do a limit as x approaches negative infinity of f of x. Well, for this one, it's still the same function, right? It's still the 9x, I think it was 9x squared plus 2 inside of a square root over 4x plus 3. And I'd still like to divide everything by the square root of x squared, which was the absolute value of x. But this time, x is now less than 0. And if x is less than 0, that tells me that the absolute value of x is equal to the opposite of x. This is the other half of the definition of absolute value. Okay? If you're not familiar with that algebraic definition of absolute value, you need to go back and review that. But it says exactly this. If x is less than 0, absolute value of x is the opposite of x. And it says this, if x is greater than or equal to 0, absolute value of x is x. So we're using that definition here. But when I divide by square root of x squared, which is effectively dividing by absolute value of x, really what I'm doing is I'm dividing by the opposite of x. And so I can't just go in, write my limit out here now. the limit as x approaches negative infinity, of the square root of 9x squared plus 2. Right, when I do my x squareds here, that's fine. But when I have my, I don't know, I believe it was a 4x plus 3, when I divide those, I can't divide them by x because I didn't divide the top by x. I divided it by the square root of x squared, which is absolute value of x, which in this case is negative x. So I have to divide these by negative x, or the opposite of x. Right? It seems a little strange, perhaps, but based on the constraint of our problem, the square root of x squared means two very different things, depending on if we're going towards infinity or negative infinity. So now our process should look the same. We get the limit as x approaches negative infinity of, well, 9x squared over x squared is still just 9. And we still have 2 over x squared. And now in the denominator, we've got a negative 4 minus 3 over x. And as x goes towards negative infinity, both 2 over x squared and negative 3 over x, this is all just approaching zeros. So we end up with the square root of 9, which is 3 over negative 4. Or we end up with a horizontal asymptote of y equals negative 3/4 to the left. And so we'll just take just a second here and flip back over to Desmos. And if we put in square root of, what do we have? We have 9x squared plus 2, and we were dividing that by 4x plus 3, I believe. This is what our function looks like. And if I graph, we'll just put it in, y equals 3/4 and y equals negative 3/4. We should see on the right-hand side here, those two values are approaching each other as we go larger and larger and larger, right? 3/4 and our function are approaching each other. But if I look over here on the left-hand side, as I go towards negative infinity, the function and negative 3/4 are approaching each other. So we can see that we do have different horizontal asymptotes in the opposite directions. Kind of cool. Now, I did say we could kind of look at this in a slightly different way, and we'll just kind of briefly touch on this. I kind of like this method that we just did better. But let's say I was looking at the limit as x approaches infinity of square root of 9x squared plus 2 over 4x plus 3. I'm going to kind of just take a little shortcut here this time, which isn't great to do, but it works. It's effective. I think about, as x goes towards infinity, 9x squared is just so significantly large by comparison to 2. Just like 4x is just significantly large in comparison to the 3, that I can really just kind of think about these as these things become insignificant as x goes towards infinity, right? These are insignificant as x approaches infinity, or as x approaches negative infinity for that matter, when we look at it from the other side. And so the limit that we're looking at should really just be equivalent to the limit as x approaches infinity of, well, the square root of 9x squared over 4x. And, well, what do I know about that? Well, I know that the square root of 9x squared is equal to the square root of 9, which is just 3, times the square root of x squared, which is the absolute value of x, over 4x. And since x is approaching infinity, right, we said if x is approaching infinity, x is greater than 0, so the absolute value of x is just x. So this just becomes a limit as x approaches infinity of 3x over 4x, which is just the limit as x approaches infinity of 3/4 when you simplify the x's, which is just 3/4. And if I were to do this towards negative infinity, see if I can still remember what this function is. Square root of 9x squared plus 2 over 4x plus 3, I hope. Right? Well, the same idea, that 2 and that 3 become insignificant, right? As x goes towards negative infinity, those become insignificant. So I can just rewrite this as a limit as x approaches negative infinity of, same thing, square root 9x squared over 4x, which is a limit as x approaches negative infinity. Note again, I'm writing limit each time until I evaluate. Don't forget to do that. Right? Of 3 absolute value x over 4x. Well, this time x is negative because x is approaching negative infinity. Therefore, the absolute value of x is equal to the opposite of x. Therefore, this limit is now the same as the limit as x approaches negative infinity of negative 3x over 4x, which I can cancel those x's. And the limit of a constant is just constant. And we can see we still get positive 3/4 to the right and negative 3/4 to the left. So just another way to look at it. This is a much more formal way to do the limit, right? These methods where we didn't actually like just eliminate the 3 and the 2. But this also works out as well. Okay? All right. So when we are using limits to find horizontal asymptotes, I've already mentioned this, you got to check what happens as we approach infinity and as we approach negative infinity. And I've mentioned this also that horizontal asymptotes for rational functions are always going to be the same in both positive and negative directions, to the right and to the left. But if you're proving that the asymptote exists, you need to show the limit in both directions. If it's free response, like you absolutely 100% have to. If it was multiple choice, you can just kind of make use of the rules that we hopefully already know from previous math classes about horizontal asymptotes. So first of those rules is if the degree of the numerator and the degree of the denominator are the same, the horizontal asymptote is the quotient of the leading coefficients of each. So if we go way back to the very first problem, not very first, but the second problem we did, we had the same degree. And so all we really have to do to find that horizontal asymptote is divide the leading coefficients. Divide 2 by 3, right? We got y equals 2/3. So that's the first rule. Second rule here is if the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote for a rational function will always be 0. So let's see here if we can find that one. I think this is that one. So our degree of our numerator was 2. The degree of our denominator was 4. So degree of numerator less than the degree of denominator, we ended up with y equals 0. And our last rule was the reverse of this, which I'll just show it here since I'm down on this page, near this page. If the degree of the numerator is more than the degree of the denominator, there will be no horizontal asymptote. So degree of numerator was 3, degree of denominator was 2, no horizontal asymptote. Right? So those are rules that you should already be familiar with. Right? 1, 2, 3 right down here. If you're not, you're going to want to memorize those rules because it will make your life easier. Sometimes they do ask about horizontal asymptotes in the multiple choice, and then you don't have to go through the whole limit process that we did. You can just use those rules if it's a horizontal asymptote in a rational function. All right, so we're going to just change gears just a little bit here. We're still going to be talking about horizontal asymptotes and what happens as a function approaches infinity. But, well, there's one thing that we haven't really formally done yet, and that's talk about, well, the formal proof that a limit exists as we're approaching infinity or as we're approaching negative infinity. And so just like I did with the vertical asymptote ones, I only showed it the formal proof for the infinity. I'm going to do the same thing here, but the same idea applies. If we were doing this for negative infinity, we'll just, we'll instead of having a function going towards infinity, we'll have the function going this way towards negative infinity. And our value for, instead of x being greater than n, x is going to be less than n, right? Because we want to be going away from the origin, right? Going towards positive or negative infinity in this case. So our rule is if a limit as x approaches infinity of f of x equals L, that means that for any epsilon I choose, or for every epsilon I choose, no matter how small of an epsilon, there is some value in, there exists an n, and again, we're not going to use, just like we didn't use epsilon in the previous ones, we used m. For these, instead of the delta, we're going to use n, okay, capital N. So for every epsilon greater than 0, there exists a value n such that if x is greater than n, so for there's some cutoff point here called n, that for all x's over here to the right of n, our function minus the limit is always less than epsilon. Or in other words, absolute value of f of x minus L is less than epsilon greater than negative epsilon, or f of x, the function is always between L plus epsilon and L minus epsilon, right? And that's what we're looking at here. We're saying, all right, past this point right here, every x value to the right of that, our function lies between these two horizontal lines indicated by L plus and L minus epsilon. And if we're doing towards negative infinity, which we will do one towards negative infinity, it's the exact same setup for every epsilon greater than 0. There exists an n such that if x is less than n, then this is still true. So we're going to go through and do 2 or 3 of these, and then we're going to do one at the end where we kind of combine the idea of approaching infinity and it equaling infinity. So instead of actually having in this case we have an epsilon and an n with the ones where it approached infinity, we had a delta and an m. Instead of having any deltas or epsilons, we're going to do one at the end where we have an m and an n, and we'll work through that. We'll work through that when we get to it. So let's start off by seeing if we can prove that the limit as x approaches infinity of 1 over x plus 2 is equal to 0. We should know that it is, right? Because if we think about this function, the degree of the numerator is less than the degree of the denominator. And our rule says for a rational function, that means that the limit must be 0. There must be a horizontal asymptote in both directions of y equals 0. So we'll start like we start all of these with a given. Our given is that epsilon is greater than 0, right? And we need to choose, instead of choosing a delta, now, which is nice, now you don't have to worry about writing that lowercase delta. We're going to choose n is equal to something. We don't know what it is yet. And we are going to suppose that, just like we had over here, that x is greater than n. And in fact, we're going to add one little thing to this that we're going to start to add a little bit more often. We're going to say that this is also going to be greater than 0, which makes perfect sense, I think, because this is a limit as x approaches infinity that we're talking about. We're talking about this as we go towards exceptionally large positive x values. So it would stand to reason that both x and n are going to be values greater than 0. Okay? And so now we need to find a way to deal with the absolute value of our function f of x minus the limit, right, which is just 0. So normally I wouldn't write that minus 0, but just since we're talking about absolute value f of x minus L, I'm going to include the minus 0 for us for now. If you don't include that, not a big deal, but if the limit isn't 0, make sure you include it. Otherwise, you're going to end up with a big old mess that's not going to work out. So if x is positive, which we know it is because we're approaching infinity, right? In fact, let's write this. Let's say this is just equal to absolute value 1 over x plus 2. Let's get rid of the 0 for now. If x is positive, then x plus 2 down here in the denominator is also positive. And if I take 1 and divide by a positive, that's still positive. And if I take the absolute value of a positive number, that just gets rid of the absolute value. So absolute value of 1 over x plus 2 is actually just the same as 1 over x plus 2. Right? Well, we're really almost done, even if it doesn't quite seem like it. Because all we really need to show is that this thing here is less than epsilon, right? And so all we really need to do is kind of manipulate this around a bit. We know that if x is greater than n, then well, we have an x plus 2, right? Let's think about x plus 2. If x is greater than, then x plus 2 is greater than n plus 2, right? If I add 2 to both those things, that should stand to reason. And then I should just be able to, in order to turn x plus 2 into 1 over x plus 2, all I really need to do is take a reciprocal of both sides, which we've done this multiple times earlier in this unit, which means that what do we have to do with our inequality sign? Well, we have to flip our inequality sign. So we got 1 over x plus 2 is less than 1 over n plus 2. Oh, well, I have 1 over x plus 2. That's just 1 over, it's less than 1 over n plus 2. Perfect. Good? Well, we have two options here. One is say, okay, cool, we're done, right? And just say, let's do that. Let's just say, okay, cool, we're done. Let's just say that this is our epsilon, right? So I'll do this off to the side. If we want 1 over n plus 2 to be our epsilon, because we just need it to be less than epsilon. Now we're less than something all in terms of that n. So if I do this, that tells me that 1 over epsilon is equal to n plus 2, or that n should be equal to 1 over epsilon minus 2. And so that's really all we have to do there. We could just say choose n is equal to 1 over epsilon minus 2, right? Hopefully you're all okay with that. Just multiply by n plus 2, divide by epsilon, and then subtract the 2. So this is one option, and we'll write this here. This is less than 1 over n, which is 1 over epsilon minus 2, plus the 2, which is just 1 over epsilon, which is just epsilon. And so really that's it. That's good enough. Now, this is not a super elegant choice for n, 1 over epsilon minus 2, but it works. So let's, I want to see if we can actually make a slightly more elegant choice here real quickly. So I'm going to kind of go to the next page. We had absolute value 1 over x plus 2 was equal to 1 over x plus 2 because we knew x was positive. And then we came through and we said that was less than 1 over n plus 2. And so that's less than 1 over n plus 2. And then we stopped and we said, okay, that's epsilon. Well, we don't have to do that. We don't have to stop there. We can actually make this look even cooler. Look even better, even simpler. If we think about how fractions work, right? If I have this value in here where I know that I've got n plus 2, I should be able to relate that to just 1 over n, right? Because I know that n is a positive number, and so if I take a positive number and add 2 to it, right, I'm getting a bigger number. Right, well, if I take 1 and divide it by a number, in fact, we'll just write this here. We know that n plus 2 is greater than n. Right? If n plus 2 is greater than n, well then 1 over n plus 2 must be less than 1 over n. True? Definitely. So really, I could just say, okay, well now 1 over n plus 2 is less than 1 over n. And now I can say, well, that even makes the arithmetic easier. Now I could have just chosen n to be just 1 over epsilon, because then this would become 1 over epsilon, which is epsilon. And it still all follows that the thing that I needed from the beginning was this, was less than this, is less than this, which is epsilon. And so you might see different choices for n or choices for delta in my answer keys than what you end up getting, right? Because I may have done a little something extra to just make my choice for n a little bit simpler, or I might not have, and you might have, right? And that's okay. So as long as you followed through and logically not broken any math rules, your answer should end up being okay, right? So just keep in mind there might be different answers that still work out. All right, so 2 different options on this one. So let's take a look here at this next one. The limit as x approaches negative infinity of 1 over x plus 2 equals 0. So it's same function, same result, it's going to equal 0, but this time we're going to do it in the opposite direction, right? We're going towards negative infinity. So let's just start with our given. Let's say our given that epsilon is greater than 0, we're going to choose some n. You know, we don't know what that n is going to be. We'll choose some n. Now this time, we're gonna start with actually the fact that x is going to be less than n, right? And what I'm going to do is I'm going to throw on the little extra added stipulation here, and you'll see why. Instead of saying that it's less than 0, I'm going to say that it's less than negative 2. Now, normally we could say just straight up that, less than 0. That's, because we're going towards negative infinity. But if I'm going towards negative infinity, I must be less than negative 2 as well. And the reason I'm picking negative 2 is, well, because I need to then deal with 1 over x plus 2 inside of an absolute value. And if I know that I'm less than negative 2, then the thing inside of here is always going to be negative. If I was only less than 0, then sometimes the thing inside of here is still positive. But if I'm always less than negative 2, the thing inside my absolute value is negative, which means to take it out of the absolute value, I just need to put a negative sign in front of it. So my absolute value of f of x that I'm looking at here should really be just negative 1 over x plus 2, right? And we know that, x plus 2 is less than n plus 2, right? Because, we knew that x was less than n. Therefore, if I add 2 to both of them, I must get an equivalence inequality. And I should then be able to just deal with this by taking a reciprocal. 1 over x plus 2 is now greater than 1 over n plus 2. And from there, all I really have to do is then multiply both sides of this inequality by a negative to end up with this function, which is what I need to find a relationship with. So if I multiply both of these by a negative, I'll end up with negative 1 over x plus 2, which is what I've got, and I'll end up with negative 1 over n plus 2, but it's no longer a greater than, it's now a less than sign, because we've multiplied both sides by a negative, and therefore I can say that negative 1 over x plus 2 is less than negative 1 over n plus 2, and now I've shown that my function is less than something, all in terms of n and some constants, and I can just call that something my epsilon. I'm not going to go through that process of making it look a little more elegant this time. We're just going to go with, let's let epsilon be negative 1 over n plus 2, which if I multiply those, cross-multiply those, I end up with n plus 2 equals negative 1 over epsilon, or effectively n is going to be negative 1 over epsilon minus 2. And so we'll just say this is equal to negative 1 over my n, negative 1 over epsilon minus 2, plus 2, which is epsilon, right? If I do negative 2 plus 2, that's 0. And negative negative cancels out, and 1 over epsilon is just epsilon. It sort of looks like an epsilon. Good enough. Not really good enough. Let's make it actually look nice. 1 over epsilon. Yeah, and so that works out, I think, pretty straightforwardly there for that one. And so the only major difference here is that, instead of saying x greater than n, we did x less than n. And we put that constraint of negative 2 on it just so we can make this logical jump. And it's obviously, it's fine to have those be less than negative 2 because we're approaching negative infinity. Obviously, they're going to be. All right, we'll do one more of these that involves an epsilon and an n before we get into just the m and the n1. So we want to prove that the limit as x approaches infinity of x over 2x plus 1 is equal to 1/2, which we should know because if we look at this is a rational function and the degree of the numerator and denominator are the same, so just divide the leading coefficients, should get a half. But let's prove that this is true. Let's prove that given any epsilon greater than 0, we can choose a value for n such that absolute value of f of x minus our limit, now the other ones were 0, but this one's not, so don't forget to put that minus 1/2 there inside your absolute value, is less than epsilon eventually, right? We're going to get there. We have to manipulate our thing before we can actually get there, though. So let's just start off with some basic simplification here. Do a little bit of it in the same row. I gotta get a common denominator, so I gotta multiply the first part of this fraction by 2 and the second part of the fraction by 2x plus 1 in both the numerator and the denominator. So if I multiply the first one by 2, that's going to give me a 2x. And if I multiply the second one by a 2x plus 1, that's going to give me minus the quantity 2x plus 1. Make sure you put that 2x plus 1 into parentheses as you bring it all together into one nice little fraction there. And then we'll combine things together there, and we'll go down another line here. 2x minus 2x cancels out, and then the minus the 1 as you distribute that negative sign through is just going to give you a -1. So we'll have -1 inside of our absolute value. We'll have 2, and we'll have 2x plus 1. Hopefully so far, so good. Yeah, we're going to do this the inelegant way, I think, first, and then we'll do a nicer, more elegant way to look at it in a bit. So let's just do a little work off to the side. Oh, and I forgot something important here. Actually, now that I think about it, I forgot to write, okay, if x is greater than n, which is greater than 0, that's bad. I should always start these off with that. So given epsilon greater than 0, choose an n equal to whatever, such that when x is greater than n is greater than 0, absolute value of f of x minus L is eventually less than epsilon, right? It was what we were trying to do. I forgot this. Need to include this. This has got to be true too. That's our suppose. So if I'm supposing that x is greater than n, well, let's kind of think about what we got going on down here. We've got a 2x plus 1 in our denominator. So somehow I want to relate 2x plus 1 with n. Well, if I know that x is greater than n, then I must know that 2x is greater than, that didn't come out right. 2x is greater than 2n. Must be, right? And well, I could just then add 1 to both of those, and that would tell me that 2x plus 1 is greater than 2n plus 1. And that would then also tell me, if you take some reciprocals, that 1 over 2x plus 1 is less than 1 over 2n plus 1. Which should be great, right? That's all good stuff. I can real quickly say, well, if I have absolute value of -1, that's just going to be, I can ignore that -1 that's in there. It just becomes a +1. I can just kind of, I can just sort of yank that all outside of the absolute value. This is the same as 1 over 2 times 2x plus 1, right? Because I know that x is positive, therefore 2 times 2x plus 1 is positive, and the absolute value of the -1 is just 1. And this should then tell me that this is less than 1 over 2 times 2n plus 1, right? Because I know that 1 over 2x plus 1 is less than 1 over 2n plus 1, so I'll just replace my 1 over 2x plus 1 with a 1 over 2n plus 1. And now, very inelegantly, we should recognize that now I just need to make this equal to my epsilon. All right, let's just say epsilon is equal to 1 over 2 times 2n plus 1. Well, if we're going to try and solve that thing for n to figure out what we choose for n, that's fine. So we should, I guess the first thing would be to just say this is 2 epsilon times 2n plus 1 is equal to 1. And I guess we divide by a 2, might as well divide by a 2 epsilon. And then we got to subtract a 1. Let's see here. This is kind of a mess. So we end up with, well, I'll just say 2n plus 1 is equal to 1 minus 2 epsilon. And then, is that right? 2n, sorry, not 1 minus 2 epsilon, but 1 over 2 epsilon. I don't know why. That's not good. Equal to 1 over 2 epsilon. And then from there, we'll subtract 1 and divide by 2. So we end up with n is equal to 1 over 2 epsilon minus 1 all over 2. What a mess, right? We could get a common denominator and simplify it if we wanted to, but we're doing the inelegant way anyway, so why bother? I'm not going to write the whole steps out here. This is epsilon. We did the right arithmetic there. Right, so if I replace the n with 1 over 2 epsilon minus 1 over 2 right here and undo that, I'm just going to end up with an epsilon in the end. Right? Now this works. It's proven it, right? We just need to choose our n to be 1 over 2 epsilon minus 1 over 2. But it's really quite inelegant. So what I'm going to do is I'm going to say we all got here, I hope, okay, right, to 1 over 2 times 2x plus 1. So let's just, if we'd gotten to there, we'll just pretend we did all that same work, 1 over 2 times 2x plus 1. That's the same as 1 over 4x plus 2. Right, and so we're going to do a little extra work from here. Just thinking about how fractions work. All right, 1 over 4x plus 2, well, if I had just 1 over 4x here, remember we're dividing by something. So 4x plus 2 is more than 4x, right? So if I divide by 4x plus 2, I'm dividing by a larger number, which means that the result is going to be smaller. So 1 over 4x plus 2 must be less than 1 over 4x. Well, by the same logic, if I'm multiplying something by 4, right? If I look at the comparison between 1 over 4x and 1 over x, 1 over 4x is going to have a larger denominator, which means that the overall fraction is going to be smaller, which tells me that this whole thing is less than 1 over x. Well, and from the beginning, I knew that x was greater than n. Therefore, 1 over x is less than 1 over n. So this is just less than 1 over n. So really, in reality, all I needed to do was choose epsilon, or, if my epsilon is 1 over n, right, then that tells me that I just need to choose n to be 1 over epsilon. So we would choose n equal to 1 over epsilon. Far more elegant than 1 over 2 epsilon minus 1 over 2. And because now I just have a 1 over n, which is 1 over epsilon, which is epsilon. And the arithmetic takes a whole heck of a lot easier. And so this is a much more elegant way to do it, but if you do it the other way, that's fine. If you see this nice progression along this way, well, that's even nicer. It'd be really great if you did that way. But if not, the other way is perfectly acceptable as well. All right. Our last one, in fact, I think this will be our last quote-unquote delta epsilon proof of the entire unit. So now this one's not going to have actually, I call it a quote-unquote delta epsilon proof because this one's not going to have any deltas and it's not going to have any epsilons. Right? When we deal with an infinite idea, right, our epsilons turn into m's and our deltas turn into n's, and that's just fine. So we want to prove that the limit as x approaches infinity of x squared plus 1 over x plus 1 is equal to infinity. It's just a rational function. So we should know from our previous rules that since the degree of the numerator is more than the degree of the denominator, it should come out to be that there's no asymptote, and this should come out to be infinity. So let's see if we can prove that. Given an m greater than 0, we need to choose an n, which we don't know what it's going to be, but we'll choose n equal to something. And we're going to suppose that our values of x, right, if x is greater than n, and normally we'd say that's greater than 0. So, well, we don't need to bother to write that for now. We'll deal with that in a little bit. So let's see then if we can go through this process and show that, you know, regardless of whatever we choose for our value for m, that are, you know, that we should end up with something. When we choose our n, we should end up with something that is greater than m in the end. I'll do my best to enunciate my m's and my n's. So for whatever n we choose, we need to show that, you know, our function is greater than m. So let's go through and do that. So we're going to think about an absolute value of f of x. And we're not going to subtract L from it this time, right? Because we don't have a limit. Our limit is infinity, right? And we're just showing that this thing needs to be greater than m. And so let's just go in, and since we're talking about x values going towards infinity, we can put any sort of constraint that we want to on what we want x to be greater than. And let's just say that we want this thing to be the smallest value that's going to kind of be useful for us here is probably, let's say x is greater than 1. Now we could use a different value, say x is greater than 2 or greater than 1,000. I'm just going to say x is greater than 1, kind of like we've always sort of done. And there's a lot we're going to have to kind of piecemeal together here. And a lot of this just requires some practice in doing problems similar to this a lot of times. But I'm going to look at what happens if I know that x, in fact, I'm going to do this in a different color. What happens if I know that x is greater than 1? Well, something that I could do to both sides of this is I could add x to both sides, right? There's nothing wrong with this, I hope, which tells me that 2x is greater than x plus 1. And we're going to note that, in fact, I'm going to do this right here. We're going to say that the absolute value of x squared plus 1 over x plus 1, as x goes towards infinity, is just equal to x squared plus 1 over x plus 1. And so now we can see we've got a correlation here that 2x is greater than x plus 1, and I have an x plus 1 in my denominator of what I'm working with, and I have this x plus 1 here. So let's just go through, and let's take some reciprocals, just like we've done many times before. I'll go back to my red pen here. So we've got 1 over 2x is less than 1 over x plus 1. And that should then tell us that you know, x squared plus 1 over x plus 1 ought to be greater than, since 1 over x plus 1 is greater than 1 over 2x, this ought to be greater than x squared plus 1 over 2x. And x squared plus 1 being over 2x being greater, well, being less than this x squared plus 1 over x plus 1 is great. This thing here ought to be also greater than something with a smaller denominator, right? If I have a larger denominator, a larger fraction, right? If the denominator, larger numerator means larger fraction, right? If the denominators are the same, larger numerator, larger fraction. X squared plus 1 is larger than x squared. So this must be greater than x squared over 2x. Well, why is that useful? Well, now we can just use a little bit of simplification. I can cancel an x there, just so long as x isn't 0, which it's not because x is well, we already said it's greater than 1, but it's approaching infinity. So this is equal to just x over 2. And if x is greater than n, then x over 2 ought to be greater than n over 2. Well, great. We know what to choose for our n now, right? We want this to all be greater than m. So if m is n over 2, that would tell us that n is 2m. So I'll just choose n equal to 2m. This gives me, well, if n is 2m, this is 2m over 2, which is m. And I've now shown that given any m greater than 0, if I choose the n value to be double that m, as long as I'm going x larger than n, for any x larger than n, the absolute value of my function, absolute value of f of x, which is this, is greater than this, which is greater than this, which is this, which is greater than this, which is this, which is m. So my function is greater than m, right? Greater than any m, no matter how large of an m I choose, right? As long as I go n equals double that m value over, I'm still going up and beyond that constraint of m that I tried to put on it. And so that should prove this last delta epsilon, which isn't a delta epsilon proof, it's an mn proof. So I know we've been going for quite a while today, but we're going to keep moving this time because we're still dealing with limits as we approach infinity with what we're going to look at next. We should be, I hope, familiar with the function e to the power of x. If you're not familiar with e to the x, you need to be familiar with e to the x. Let's get rid of all this stuff we've done here before. E to the power of x, you should be very familiar with it. It looks like that, right? As x goes towards infinity, it goes up towards infinity. As x goes towards negative infinity, it approaches the horizontal asymptote of 0. And if you're not familiar with that, you need to know the graph of e to the x. Right? So the limit as x approaches infinity of e to the x, well, we just saw it's going up towards infinity. You want to remember that limit as we approach infinity of e to the x is infinity. Right? Down here, as we approach negative infinity, this one, for e to the x, we just saw that is 0. We should know that, right? It should make sense, right? Because if I tried to plug negative infinity in there, I get e to the negative infinity. Well, what does that mean? That means 1 over e to the infinity. Well, 1 over a huge number is 0. Same here, e to the infinity. Well, if I take a number, e, that's larger than 1, and raise it to the infinite power, right? If I just multiply it by itself over and over and over and over and over again forever, it's going to get huge, right? Without even knowing what e to the negative x looks like, we should be able to say, oh, this is the same. This is e to the negative infinity, so this one should be 0. And this one is e to the negative infinity, or e to the infinity, so it should be infinity, right? And we should know, I mean, you should know what happens if you change that into a negative x, right? Just, you're going to flip it right across the y-axis, and we can see that as we go towards negative infinity, it goes to positive infinity. As it goes towards positive infinity, it should go towards 0. Right, so you should be familiar with what that graph looks like too. But if not, make sure you know the limits. So we're going to use these 4 limits that we now know to investigate a bunch of other limits. Right? Starting, well, right here, with determining if this has any horizontal asymptotes, 2 over 1 plus e to the x. And so this is not a rational function, which means that we don't know what's happening on either side. It might be different on both sides. So again, be very careful to check our limit as x approaches infinity of 2 over 1 plus e to the x, and our limit as x approaches negative infinity. So we'll start with infinity. And if we do that, we end up with 2 over 1 plus e to the infinity. Well, we just said e to the infinity is infinity. So this is 2 over 1 plus infinity. Well, 1 plus infinity is just infinity. And if I take 2 and divide by an infinitely large number, I should get an infinitely small number. I should get something very close to 0. So we should see that this has a horizontal asymptote of y equals 0 to the right. And if I were to do this as I approach negative infinity, I then should look at this as if this is 2 over 1 plus e to the negative infinity. Well, e to the negative infinity, we just talked about that. That's like 1 over e to the infinity. That's just like 0. This is just 2 over 1 plus 0, which is just 2, which tells us it should have a horizontal asymptote of y equals 0 to the left. And if we were to go in, we'll go back in real quick to Desmos and look at the function 2 over 1 plus e to the power of x. We can see that as we go towards the left, clearly approaching 2. And as we go to the right, clearly going right along the x-axis there, approaching 0. Right? This is function 2 over 1 plus e to the x. All right, let's look at this other function here. We got the limit as x approaches infinity of e to the power of 6 minus 2x minus 5x squared. Well, I don't know what that function looks like. I could probably come up with a basic idea of what it looks like, but I couldn't tell you exactly what it looks like. But I should be able to tell you what its in behavior to the right is, just by using those original 4 limits that we first talked about. Let's make a quick u substitution. Let's let u equal 6 minus 2x minus 5x squared. Well, as x goes towards infinity, what happens to 6 minus 2x minus 5x squared? Well, one piece of this dominates the rest of it, right? The x squared piece is magnitude larger than the 6 or the minus 2x as x goes towards infinity. So really, this 6 and this minus 2x, these are insignificant by comparison. And so what happens to negative 5x squared as x goes towards infinity? Well, infinity squared is infinity, and negative 5 times infinity would be negative infinity. So really what we're looking at here is u is approaching negative infinity if I let u be that exponent. So this ends up becoming a limit as u approaches negative infinity of e to the u, right? Well, that's just e to the negative infinity, which is just equal to 0. So we should see, I guess I can write it up here too, our limit as x approaches infinity of e to this really lovely looking power there, whatever it was, 6 minus 2x minus 5x squared. As x goes towards infinity, it should be approaching 0. Then we'll take a look at another one similar to that. We'll do the same process here. We'll just let u equal x to the 4th minus 2x plus 1. And as x goes to negative infinity, the part that dominates is the x to the 4th, and the minus 2x and the plus 1 are insignificant by comparison. And so negative infinity to the 4th is just positive infinity. So this limit becomes a limit as u approaches infinity of e to the u. Well, that's just e to the infinity, which is just infinity. And I think maybe this will be the last one of these. Maybe do 1 or 2 more of these. Same idea. Let's let u equal 2 plus x cubed. And as x goes to negative infinity, what does u go to? Well, the dominating piece is the x cubed. And if I cube a negative infinity, u is still going to be approaching negative infinity. So this is now just a limit as u approaches negative infinity of e to the u. That's e to the negative infinity, and that's just 0. we're looking at a limit as x approaches 0 from the right. Now this is a little different. We're not actually looking at an infinity one here, but it's going to be in a second. For e to the 1 over x, let's just do the same idea with the u sub. Let's let u equal 1 over x. And then, well, as x goes towards 0 from the right-hand side, that means we're plugging in very small positive numbers for x, which means this becomes 1 over a very, very small positive. Right, a very, very small positive. Well, 1 over a very, very small positive is a very large positive. So u is actually going to be approaching infinity. If this was a limit as as x approaches 0 from the left, then we'd end up with u would be approaching negative infinity, because it'd be 1 over a very small negative number. But we had small positive here, so we'll have positive infinity. So this becomes a limit as u approaches infinity of e to the u, which is just e to the infinity, which we know is just infinite. It's just infinite. We're getting closer to the end here. We're going to do a couple more with e, and then we'll have to do a couple problems where we deal with some logarithms, and then we'll kind of piece a few of those together and be done. We got, I don't know, 6, 7, 8 more problems to do. Kind of a long day today. So we've got a limit as x approaches infinity of this whole big mess of a string of things. E to the 10x minus 4 e to the 6x plus 3 e to the x plus 2 e to the negative 2x minus 9 e to the negative 5x. Which, if I plug in infinity, I get infinity minus infinity plus infinity for all those, plus, ooh, this one's e to the negative infinity. So that's actually plus 0 minus another one that's 0. Infinity minus infinity plus infinity, right? Infinity minus infinity. This was one of our indeterminate forms that I mentioned a week or two ago. This is another indeterminate form. So to really officially show this limit, we really need to do some extra algebraic work. Now, we should, I hope, recognize that e to the 10x dominates e to the 6x, and that infinity from e to the 10x is going to be more than the value from the e to the 6x. And really this should, we hope, end up becoming infinity in the very end. But the right method for this is to just factor out the e to the 10x from everything. Because if I do that, I'm no longer going to have multiple infinities. I'm going to have one infinity out in the front multiplying things, but I'm going to end up with just, well, if I factor e to the 10x out of e to the 10x, that's just a 1. And if I factor e to the 10x out of negative 4 e to the 6x, that should be negative 4 e to the negative 4x, right? I have to add the exponents, e to the 10x, e to the negative 4x. If I add 10x and negative 4x, I should get 6x, right? So I can factor that out. And same here, I'm going to do plus 3e to the, that one's going to have to be a negative 9x. And I don't really have to do it with the 2e to the negative 2x and the 9e to the negative 5x because they were just 0. I could leave them out of this factorization and just call them 0, but I might as well. Let's do 2e to the negative 12x and minus 9e to the negative 15x. Right? And so now, if I plug in infinity, this is just infinity times 1 minus, well now, if x is infinity, all these negative exponents yield a bunch of zeros. Minus 0 plus 0 plus 0 minus 0. And infinity times 1 is just infinity. And with this next one, same idea is going to apply, except now we're approaching negative infinity. So right off the bat, the ones with positive exponents are actually the ones that are zeros. This is 0 minus 0 plus 0. But then this becomes plus infinity minus infinity, which is indeterminate. So we'll do our little bit of extra work, which in this case, when we're approaching negative infinity, we're going to flop this around. Instead of factoring out the largest positive exponent, we're going to just factor out the largest negative exponent. So I'm just going to take out a e to the negative 5x. And that leaves me with e to the 15x, because negative 5x and 15x needs to give me that 10x, minus 4e to the, this time it'll have to be an 11x, because negative 5 plus 11 is 6. And then plus 3e to the 6x. And now it'll be plus 2e to the 3x, right? Negative 5 plus 3 is negative 2. And then that last one is just a minus 9. And so what we end up with here is, well, if I plug in negative infinity into e to the negative 5x, I get e to the negative 5 times negative infinity, or e to the infinity, which is just infinity. And I get all the positive exponents become 0, 0 minus 0 plus 0 plus 0, and then minus 9. Well, that's just negative 9 infinity, which is negative infinity. All right. On to the natural logs. We're getting close to the end here. So we have a limit as x approaches infinity of natural log of x. You should know about the natural log function. If you don't, let's just take a quick look at it. But really, if you've made it to a calculus class, you should know about natural log. Here's the natural log of x. Right? You can see that obviously we know we can't take the natural log of 0. That's why it drops down here to negative infinity as we approach 0 from the right-hand side. And you can't take natural log of negatives, so there's nothing to the left of 0. And then as we go towards positive infinity, right, these values are going to keep, as you'll see, keep getting bigger. They don't get big very quickly. In fact, natural log function, logarithmic functions in general, don't increase very rapidly. But what they do is they do go up forever. They increase. There's no bound on them. They increase without bound. And they do it slowly, but they do it. They do increase forever. So we should recognize here that the limit as x approaches infinity of ln x is infinity. The limit as x approaches negative infinity of ln x, well, we just talked about that. How can I approach negative infinity if there's no function there? This does not exist. The limit as we approach 0 from the right of natural log, that's the one where we're approaching this vertical asymptote going down towards negative infinity. But if I try to approach 0 from the left, well, I can't do that. There's no function on the left side over here, right? There's no function over here. So I can't have this. This limit also does not exist. So those are the 4 basic thoughts we need to have about the natural log function when we're talking about limits. And we're going to use those to evaluate a couple other limits. So we're going to look at a limit as x approaches infinity of the natural log of some quadratic mess there, 4x squared plus 5x minus 2. And we're going to treat this the same way we treated the exponential ones. We're just going to let u equal 4x squared plus 5x minus 2, and say as x approaches infinity, u is going to approach, well, infinity squared times 4 is infinity, plus 5 times infinity is infinity, minus 2 is still infinity, right? And really the only piece of it that matters is the 4x squared. That's the largest power. That's the piece that dominates it, right? So what we're really looking at now is just a limit as u approaches infinity of the natural log of u. Well, we just did that on the previous page. That limit is just infinity. And if we do the same thing down here with this one, where we let u equal 4x squared plus 5x minus 2, as x goes to negative infinity, you should still be approaching positive infinity because, again, this 4x squared term dominates, right? It's significantly larger than a 5x and a minus 2 as x gets towards negative infinity. And negative infinity squared is positive infinity. If I multiply it by 4, it's still positive infinity. So this now just becomes the exact same thing. It's the limit as u approaches infinity of the natural log of u. Well, that's just infinity. And just because it's a limit as we approach negative infinity doesn't mean, with a natural log, doesn't necessarily mean that that limit can't exist. We have to break it down to the base natural log function to determine if that one exists, right? Because if I plug negative numbers into 4x squared plus 5x minus 2, I get positive numbers sometimes, right? And therefore, I can take the natural log of some negative numbers. Okay, so that, you know, not taking the natural log of a negative, but the argument of the natural log becomes a positive for some negative x values. Now let's do another quick one of these, and hopefully we kind of got the idea on them. So, limit as x approaches negative infinity of natural log of 1 over x to the 4th minus 8x. So, let's see here. If u was 1 over x to the 4th minus 8x, we just have natural log of u. We'd have to figure out what happens as x approaches negative infinity. Well, let's see. U would be approaching 1 over something, and the dominating piece of that would be the x to the 4th. And so x to the 4th, if x is negative infinity, is still going to be infinite, right? And if I take a negative and raise it to the 4th power, that becomes a positive. So really this becomes 1 over positive infinity. I'm making an important note there that that's a positive infinity, because what we're really talking about here is 1 over infinity, which is 0. But we're talking about what happens as we approach infinity. So what we're doing is we're approaching 0. We're approaching 0, or 1 over infinity, but we're doing it from the positive side, because 1 is always positive, and this infinity is always positive, and therefore the number I'm getting is always positive. Therefore, I cannot be approaching 0 from the left-hand side. I'm only approaching 0 from the right-hand side. So as I rewrite this limit, it's very important that we think about whether this 0 that we're getting close to, are we getting close to it from the right or from the left? Because on the natural log function, right, it's very important. If I'm converting this limit into 0 from the right, well, then I can get an answer. But if I'm converting it into 0 from the left, well, natural log doesn't exist there, and I'm going to just say that doesn't exist. But for our case here, we got 0 from the right. So this just becomes a limit as x, not x. This is a u, we just changed it to u. The limit is u approaches 0 from the right of natural log u, which we know to be negative infinity. And I promise we're almost done here. One last tiny topic to talk about, and then we will do a couple problems, and then we will be done. So the limit as x approaches infinity of f of x equals infinity. Right? This is true for a lot of different types of functions, and many of them increase at very different rates. So for functions, and there are, like I said, there are 4 types of functions, basic functions, that we're going to deal with that have this quality, that the limit as x approaches infinity of them is infinity. One of them, and in fact the fastest one of them, is the exponential function. Now it's not actually the fastest one that does this, but it's the fastest one that we deal with in Calculus 1. So I'll briefly mention here, for those of you that will eventually go on to Calc 2 and deal with a bunch of series stuff, there are factorial functions. Factorial functions increase more rapidly than exponential functions. So just file that away in your brain if you're ever going to take Calc 2, that factorials increase more rapidly than exponentials. But for our purposes, exponential is going to be the fastest, followed by polynomial functions. And of course, the faster ones will be the ones with larger powers. So x to the 7,000th is going to go towards infinity faster than x to the 6,000th, which will go faster than x to the 100th, which will go faster than just x, right? A linear function. Right? And then we also have root functions, right? Like square root, cube root, fourth root, 12th root, right? So, keeping in mind, those are just like, fractional exponents, right? To the 1/2, to the 1/3, to the 1/4. So a square root is going to go towards infinity faster than a cube root, which will go faster than a fourth root, and so on. And then down to the slowest one that we'll deal with, which is the logarithmic functions, right? So logarithmic functions, just like we just dealt with the natural log, they still go towards infinity. They just do it more slowly, right? Than other functions do. Let's see, anything else to say about that? I guess the important thing to say is that the smaller the base, so like log base 2 of x is going to increase more quickly than like log base 10, right? So like natural log will increase more quickly than log base 10, which will increase more quickly than log base 100 or something like that, right? So just, if you ever are stuck in the situation where you've got different logarithmic bases, the smaller the base, the faster it increases. Okay? So just keep that in mind as well. Let's see. Well, in fact, we can write that smaller base to larger base, slower. The roots, right? We'll have like square root, cube root, fourth root in that order. Polynomial x to the 100th down to like x squared down to x. So that's in there too. And then of course like an exponential, like 10 to the x is going to be faster than 2 to the x. Right? So you can kind of keep in mind that sort of order. And that will allow us to work with some functions like these, where if I plug in infinity to this, x squared over e to the x, I get infinity over infinity, which is indeterminate. But I don't have a good algebraic way to deal with this. I just have to think about my little chart that I just made. Which of these things gets bigger faster? Well, e to the x gets bigger faster, which effectively means that I've got a larger denominator than I do a numerator. Well, if the denominator is larger than the numerator, that thing is less than 1 and more than 0. And as the denominator gets bigger faster, it's getting smaller and smaller and smaller, which means it's going to start approaching 0. So if the denominator goes towards infinity faster than the numerator does, we end up with 0. But vice versa, this is still infinity over infinity, but this time the denominator is slower than the numerator. Right? We're going to infinity faster in the numerator this time, which means that this fraction is a larger number over a smaller number. It's getting bigger, and as the numerator gets bigger and bigger and bigger, more quickly than the denominator does, we're just going eventually towards infinity. And even though this function, x to the 2,000 over 2 to the x, it starts off, x to the 2,000 is much bigger than 2 to the x for some even some relatively large values of x. As x goes towards infinity, this denominator, which is going towards infinity, just like the numerator is, the denominator is going towards infinity faster as x goes towards infinity, meaning our denominator is bigger than our numerator, meaning that this limit should be 0. And this is sufficient enough work to show that for now. We're going to have another technique once we get through somewhere in the middle of our third unit here, that allows us to kind of see this in a nice new light. But for now, this is going to be good enough. And sometimes these show up in the multiple choice, and it's just nice to be able to look at it and be like, oh, numerator is increasing more quickly than the denominator as they both go to infinity, so it's infinity. Or denominator is increasing more quickly as they both go to infinity, so it must be 0. And that is going to be it for today. Next time, we're going to start going into some of our discussions about continuity. We're actually getting very close to the end of this whole unit. So we'll start talking about continuity next time. And we may finish up next time. We may break it up into 2 different lectures, but that is it. A good solid hour and a half today. And we're going to end it there.